Consider water droplets falling on a calm water surface. As it falls, it creates a disturbance which travels in form of circular rings before eventually disappearing altogether and reverting to a calm water surface. We can visualize this. When the droplet fell, it created an upward and downward disturbance. All water molecules participate in this disturbance to move up and down in form of circular rings. It appears as though these rings start from the center and radiate outwards. Key point to note is that we can see regions where water level is raised like a mountain and lowered like a valley. In this case, the blue circle marks a line where the water particles are at their highest point and appear like a tall mountain. On the other hand, the yellow circle marks a line where the water particles are at their lowest point and appear like a valley surrounded by tall mountains. As water molecules move up and down, we can say that this is a transverse wave. The point at which water molecules are at their highest level is called crest, marked by white lines, while the point where water molecules are at their lowest point is called trough, marked by the blue lines. The disturbances caused by water molecules are called ripples, and these ripples are circular in nature. They radiate out from the center to the edges of the frame. Crest and trough are present as the ripples move out from the source. Let us mark blue lines on the region where water level is at the highest point. We get concentric blue circles as shown. All of these blue circular lines represent the region where water molecules are at its highest point. In other words, they represent water molecules in the crest position. Those lines that connect points on waves that are in the same position are called wavefronts. If these lines represent water molecules at their highest point, then the colored region represents water molecules at their lowest point. In other words, they represent water molecules in the trough position. So as water wave moves from left to right, we get the water molecules at the highest point known as crest and lowest point known as trough. We drew a circular line on those points that were at their highest point and got concentric circles. Similarly, if we join all the points that are on the crest, we get a straight line. This straight line is known as a wavefront. A wavefront is defined as an imaginary line that connects all points that are in phase. In other words, those points on different waves that are in the same position and oscillating in the same pattern. In this case, we drew the wavefront line on successive peaks of different waves. We drew wavefront on successive peaks on different waves, and we know that the distance from one peak to the next is called wavelength. So wavefront and wavelength are related. Distance from one wavefront to the next is equal to one wavelength, that is horizontal distance of one peak to the next. The horizontal distance from one crest to the next trough is equal to half the wavelength. Therefore, half the distance from one wavefront to the next is equal to half the wavelength. So if we remove the waves, we get a clear picture. Distance from one straight line, also known as wavefront, to the next is equal to one wavelength, and half this distance is equal to half the wavelength. If wavefronts are imaginary, why use them at all? It has to do with the ease with which we can represent the waves. Consider multiple waves traveling from left to right. It might be difficult to represent them visually perfectly. Now consider the case in which we can represent the wave motion by straight lines moving from left to right. These straight lines join all the points that are on the peak of the wave, therefore represent wavefront. I'm sure you'll consider drawing straight lines a lot easier than drawing wave patterns, and that is why we use wavefronts to represent waves. Now let us attempt few practice problems concerning wavefronts. In the image, we are given the distance from first wavefront to the last wavefront as 20 centimeters, and we are required to determine the wavelength. Remember, the distance from one wavefront to the next is equal to one wavelength. Therefore, there are total 5 wavelengths between the first and the last wavefront. 5 wavelengths are equal to 20 centimeters. Therefore, one wavelength is equal to 20 divided by 5 equals 4 centimeters. In the second problem, we are given a set of circular wavefronts. For K, lies on the wavefront, while curve P lies between the two wavefronts. We are also given the displacement time graph for A and are required to sketch the displacement time graph of P. From our lesson, we should know that A and B lie in the opposite position. The distance from one wavefront to the next is one wavelength, and half this distance is half a wavelength. That is, if A is the crust, then point B is the trough, and if A is the trough, then B is the crust. So, the displacement time graph for B is the exact opposite to that of A. When A is at its highest, B will be at its lowest. Similarly, when A is at its lowest, B will be at its highest.